Welcome you all, and in this lecture, we are going to learn about the different types of point symmetries. So, let's begin with the first type, that is inversion symmetry. So, let me write. Inversion symmetry. So, what happens in inversion symmetry is like, let's take the lattice points. Yeah. So, these are the lattice points here, and now we are going to represent like the direction of the lattice points by n vector, that is a translation vector. Let me write. Okay, so we can represent these cells by the primitive vectors as we learned in the previous lectures. So this is a1 vector, and this is the a2 vector, and this is the generated primitive cells. So let's call it n vector. Now, when we are going to consider the inversion symmetry, so so after doing inversion, um, we nothing understand about the crystal change due to this symmetry. So while doing the inversion symmetry, the n vector generally becomes the minus n vector. So we can represent it in a pictorial way, like considering the same case. So basically, now the arrangement looks something like this. So this a1 vector flips in this fashion, like this one, and this a2 vector also flips in the opposite direction. So it will look something like this thing. So this is a1 vector, and this is a2 vector. So basically this is the main like key point. Now this cell will look something like this thing. So this thing is the inversion symmetry of this arrangement. So you should remember that the inversion symmetry is always present in all Bravais lattice. Let me write. Inversion symmetry is always present in all Bravais lattice. All Bravais lattice. Now let's talk about the rotational symmetry. So the order present in the rotational symmetry are can be given by the like integers n equal to 2, 3, 4, and 6, and so on. And the rotation angle can be calculated on the basis of this equation, that is theta n equal to 2 pi by n. So in rotational symmetry, you should remember that each rotation each rotation leaves the crystal unchanged. Now come to the reflection symmetry. Reflection symmetry. Um, so reflection symmetry, the arrangement looks something like this thing. So the given arrangement is divided by like plane of reflection. We can treat this as a plane of reflection. This is the plane of reflection. So due to this symmetry also, there is no any specific change in the crystal property. Um, Now we can combine the rotational and inversion symmetry as a rotation, like we can call that as a Roto inversion symmetry. Roto inversion symmetry. So in this case, rotation around axis is followed by the inversion, and there is also a combination of rotation and reflection. So we can call that it as a roto reflection symmetry. Roto reflection symmetry. So in this case, rotation around axis is followed by the reflection. Now, now in general, um, we know this property that is AB is not equal to BA, and A dot A inverse is equal to identity matrix I, and AB of C is equal to A of BC. So this above point symmetry are called groups, which constitutes 7 crystalline structures, which are called synchronous in the Breuer lattice. So if we add translation symmetry to the point group, that is point plus translation, then we have 14 Breuer lattice. Now if we consider like complex basis system, then this complex basis system leads to 32 point groups. Now if we add translation symmetry to this knee point symmetry, then we get 230 space groups. Now let's start with the classification of solid materials according to the bonding. Okay, so this is our new topic. That is classification of solid materials according to bonding. We know that the probability of finding the electron in the respective volume is given by this equation. That is psi r is equal to mod of psi r square dot dv equal to dv. So this is the probability of finding the electron in the respective volume. And we can find the charge density by this equation. That is rho of position vector r is equal to the charge multiplied by the summation over I. That is psi of phi of r vector mod of square. So you should remember that in quantum mechanics, free electron is represented by psi equal to a minus I k vector r. So this is a way to represent the free electron in the quantum mechanics. Now in terms of bonding, like we can get crystals of the following types. Like first one is metal, then ionic crystal, then covalent solids, then intermediate one, then noble gas crystal, and molecular crystal, example graphite. If we talk about metals, they have less density and their density is constant, and the electrons acts like a glue in that case, in the case of metals. Now if we talk about the ionic crystal, let me clear this thing first. Okay, so these are the cations. So in case of metals, the electrons acts like the liquid glue. So these are the electrons. So in the case of metals, electrons acts like a glue, and the metals have less change in density. That is, the change in density is very small. We can say that the density is almost constant. Now in case of ionic crystal, for example NaCl, so this is example of ionic crystals. There is a column interaction. There is one positive charge and there's one negative charge. This is sodium plus and this is chlorine minus, and there's existence of some types of Coulombic interaction. So this is the Coulombic interaction between these two atoms. Now in covalent solid, we know that the outer electrons are shared equally by the bonding atoms, and in the case of covalent solid, there's a strong oscillation of the charge density. For example of the covalent solid is silicon. Now if we talk about the noble gas crystals, the inert gas forms the simplest crystals with atoms remaining very similar to the free atoms. These elements have their outermost electron shell completely filled, and the distribution of the electron charge in the free atom is spherically symmetric. If the electron charge distributions were rigid, the interaction between these two identical gas atoms would be zero. So there would be no cohesion and solid crystals would not form. However, momentary asymmetries in the electron distribution of one atom can induce dipole moments in the neighboring atoms. So this case of solids are called noble gas crystals. So they can be represented in a similar fashion like this one. I think I created a mess here. Cool. So I can represent the noble gas crystals in this fashion. Cool. Okay. And so there's like something behavior like a dipole moment. That is delta plus, delta minus, delta plus, delta minus. So this is the representation of the noble gas crystal. So they will cancel each other. Noble gas crystal. Now there is also existence of the molecular crystal, for example graphite. Now let's talk about the binding energy and or cohesive energy of the crystal. Okay. This is the new page. Okay, let's start. Binding energy and cohesive energy of the crystal. Now suppose you can take a one crystal here, looking something like this. So just take one crystal and now break that crystal into ions. So actually you've taken the crystal and broken that crystal into ions. So the cohesive energy of a crystal is the energy that must be added to the crystal to separate its components into several free atoms at rest and at infinite separation. So whether I should write it not or not, I think I should write the definition. Okay. So the cohesive energy of a crystal is the energy that must be added to the crystal to separate its components into several free atoms, into neutral free atoms at rest. free atoms at rest and at infinite separation. So we can write the cohesive energy equal to energy of atoms minus crystal energy. So crystal binding energy can be crystal binding energy can be expressed in electron volt per atom. Now let's move on to the last topic of this lecture, that is the polarization vector. So the polarization vector is the dipole moment per unit volume. And it is represented by this expression. So the dipole moment is given by this expression, that is this thing. So when electric field is applied, we have a diatomic molecule, and we can represent the polarization vector by this thing. So this quantity here is the tensor quantity, and if there is the isotropic condition, then it becomes a scalar, and we can represent this quantity as let me write. If there is isotropic condition, then we can write that tensor quantity as in the form of scalar, and we can write it as this thing. So it's a scalar quantity. Now in the next lecture, we are going to explore reciprocal lattice. Like few lectures it will take to complete it, as it's somewhat lengthy. Now I think we have finished with the basic things which is required for understanding the solid state physics. So thank you, and from the next lecture we are going to start reciprocal lattice.